With that, we'll start this session on incredible research that has been done by Dr. Ben Santer. So, first of all, thank you for joining in. I know there is some technical glitch that we are facing now, and we are facing more people joining now. But we'll get started. We'll record the session for other people's benefit. Please, welcome me. Welcome, Ben Santer, who is atmospheric climate scientist, and he studied natural as well as human fingerprints in observed climate records. He's a lead author of a key chapter of IPCC report, the historic IPCC report of 1995. And Ben, since 1995, Ben has also identified human fingerprints in atmospheric temperature and water vapor, ocean heat content, sea surface temperature in hurricane formation regions, and many other climate variables. So today we're gonna, explore more about his research over the last 3 decades, which not only covers the surface temperature as a climate variable, but other climate variable as well, which is the contribution to our understanding of the human influence on climate change. Without further ado, may I request Ben to present your research with your presentations, please.
Thank you very much, Kishan. Can you see my screen?
Yes, I can. Thank you.
This isn't just a pretty picture. This is satellite imagery of the total amount of water vapor in Earth's atmosphere on a particular day. And those magenta blobs that you can see near Australia are very high concentrations of water vapor. You can actually see typhoons in this kind of imagery. I show this because water vapor is one of the things that we study in order to determine how and why it's changing and whether there's a human imprint on this kind of information. First of all, before I get started, I just wanted to situate us in terms of where we are today with temperature changes since 1850. This is a nice visualization from Berkeley Earth in California, one of the 4 to 5 groups that compiles measurements of surface temperature. And it shows you our best estimates of changes in global mean surface temperature month by month since 1850. The darker colors here are earlier times, and the lighter colors are later periods. And each line on this figure is 1 year. So the first year is January 1850 through to December 1850. Then you go on to 1851. And you can see over time how the planet has warmed in every month of the year. The picker is the last couple of years. 2021, 2022, and 2023 are specifically highlighted. And the last month is August of this year, and it's literally off the charts. If we were to add September and October of 2023 to this figure, they too would be at least a half a degree Celsius warmer than anything we've observed previously, any previous September or October. So this gives you some idea of the reality and seriousness of human-caused global warming. Kishan, you mentioned that I've been involved with the Intergovernmental Panel on Climate Change, or IPCC. They were set up in 1988 to advise the governments of the world about human-caused climate change, the impacts of human effects on climate, and possible adaptation and mitigation strategies. Their first report was in 1990, and it essentially said that the jury was out in terms of formal identification of a human effect on climate. Quote, "The unequivocal detection of the enhanced greenhouse effect from observations is not likely for a decade or more." 5 years later, the second assessment report of the IPCC came to a fundamentally different conclusion. The jury was in. As you mentioned, Kishan, I was in charge of the chapter of this report that came to the following finding: the balance of evidence suggests a discernible human influence on global climate. And it was the first time that the international scientific community said formally, we can identify a human-caused global warming signal. That finding back then was kind of controversial. I was investigated by Congress. There were calls for my dismissal with prejudice from my position at Lawrence Livermore National Lab. It was a difficult time professionally, but the way science works is extraordinary claims like that are tested and vetted by the entire community. And in 2001, 2007, 2013, the IPCC came out with its third, fourth, and fifth assessment reports that were much stronger than the cautious, even wimpy balance of evidence finding. The most recent IPCC report in October 2021 stated that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. So this is the arc of history, the arc of our scientific understanding of human effects on climate. What enabled this arc of history? I would argue that a number of factors did. One was, over time, we developed better computer models of the climate system. Over time, we also developed a better understanding of the factors, both human and natural, that affect climate. Not only human-caused changes in greenhouse gases, but also particulate pollution, changes in the sun's energy output, changes in volcanic material in the atmosphere. We also developed over that 28-year period from 1995 through to the present, longer and improved climate observations from space, like vapor information I showed you in the first slide. Critically, the place I worked at Lawrence Livermore National Lab in California, helped to develop benchmark simulations that every computer model of the climate system in the world had to perform. Those simulations were critically important in order to, for example, be able to look at model projections of 21st century climate change for temperature, for sea level, for many other things we care about. The climate science community also developed something called the Earth System Grid Federation, so software and hardware for sharing model simulation output, satellite temperature data, and for enabling an entire climate science community to interrogate that information. And finally, and this is what we'll talk about this morning, I think progress was enabled by climate fingerprinting. So what is climate fingerprinting? The basic premise is that different factors that affect Earth's climate, natural changes in the sun's energy output, changes in volcanoes, purely natural, human-caused changes in heat-trapping greenhouse gases caused by fossil fuel burning primarily, human-caused sulfate pollution, human-caused changes in ozone, that each one of these factors has a specific pattern of climate response. And what you see here are those patterns of climate response, or fingerprints, that are obtained from one particular climate model. And in climate model world, you can do what we can't do in the real world. You can change just one thing at a time: the sun, greenhouse gases, sulfate pollution, volcanoes, ozone, according to our best understanding of how that thing has actually changed. And in this particular model, these are the 5 fingerprints of those different factors. And you're looking here from the North Pole to the South Pole, and from the surface of the planet right up to nearly 30 kilometers above the Earth's surface. These are changes in temperature through the atmosphere over the second half of the 20th century in this particular model for these 5 different things. And I don't want to get into the details of these things. The main point is they're different. Each one of these things has a different characteristic fingerprint in atmospheric temperature. And the question is, can we use this kind of pattern information to disentangle observations of climate change and figure out the relative contributions of natural factors like the sun and volcanoes and human factors to observe climate change? So the gentleman who first started thinking about using patterns to identify human effects on climate was this gentleman, Klaus Hasselmann, formerly director of the Max Planck Institute for Meteorology in Hamburg. He looks a little bit like the country and western singer Kenny Rogers in the United States. And actually, on one flight with Hasselmann from Germany to Denver, he was mistaken for Kenny Rogers, and we got bumped up to business class. What was Hasselmann's key insight about fingerprinting? Well, he was awarded 1/3 of the share of the 2021 Nobel Physics Prize for developing, quote, methods for identifying specific signals, fingerprints, that both natural phenomena and human activities imprint in the climate. And his key insight was that instead of looking at individual points on the Earth's surface, which is what scientists were doing back in the 1970s, you needed to look at the entire pattern of climate change. So back in the 70s, with the first computer models of the climate system, scientists were increasing levels of atmospheric CO2 in these computer models, and at each grid point on the Earth's surface, they were looking at how temperature changed and trying to understand whether those changes in temperature at those individual locations were large relative to purely natural fluctuations in climate. So this is the kind of thing that Hasselmann advocated for. This is a pattern of temperature change from several dozen different climate models in response to human-caused changes in heat-trapping greenhouse gases. And without getting into the details, this pattern shows warming at every location on the Earth's surface in response to greenhouse gas increases. And the largest warming is over the Arctic, something called Arctic amplification. So back in the 70s, scientists were looking, say, over Alaska, where there was a big projected warming in surface temperature. Hasselmann said, no, don't look there, because if you look over Alaska, that's also where the natural climate variability, the month-to-month, year-to-year, decade-to-decade intrinsic noise of the climate system associated with things like El Niños, La Niñas, and many other natural modes of climate variability, that noise of climate is large over Alaska. The signal is pretty appreciable, the noise is larger, and you don't have a good chance of detecting human-caused climate change at that individual location relative to the noise of natural climate variability. But if you take a step back and look not only at that individual location, but at the entire global pattern, clearly this and this are very different. And Hasselmann said, go and exploit these global pattern differences in order to do the separation of human and natural effects on climate. So how might such fingerprinting be used in practice? Well, I'm sure you've all seen something like this. Again, this is from Berkeley Earth in California, one of the groups that looks at surface temperature. They look at literally millions of measurements of surface thermometers, ships of opportunity over the ocean, buoy measurements, more recently satellite temperature measurements of the ocean, to compile this kind of estimate of global scale changes in Earth's climate. And as you can see, since the beginning of the satellite era in 1979, We've seen profound warming of the Earth, and we're now nearly at 1.5 degrees Celsius warming relative to pre-industrial times, relative to the second half of the 18th century here. And there are folks in the United States and probably in your countries too, wherever you are joining this call from, who have argued and still do argue that all of this surface warming is natural and just due to an uptick in the sun's energy output. How might fingerprinting, looking at patterns, enable us to test that hypothesis? This obviously isn't drawn to scale here. It's just illustrative of this sun explains everything hypothesis. So imagine that since 1850, over the last 170 plus years, all surface warming of roughly 1.5 degrees Celsius now were due to a natural change in the sun. What would the logical and inescapable consequences be? More active sun, more solar radiation arriving at the top of the Earth's atmosphere. The consequence would be heating throughout the full vertical extent of the atmosphere. What do we actually see when we look at satellite measurements of temperature changes through the Earth's atmosphere? Well, this is what you see here. These are from these beautiful satellite measurements that go from close to the Earth's surface right up to 50 kilometers above the Earth's surface. And here you see for two different satellite data sets, the estimates of how Earth's atmospheric temperature has actually changed over the period that we've had these observations, roughly a 37-year period now. And the kicker is we can see warming of the lower atmosphere, the troposphere, and cooling of the upper atmosphere, with the cooling getting larger the higher up you get above the Earth's surface. This is fundamentally inconsistent with the notion that the sun explains all of the warming low down in the atmosphere. If that were true, we would expect to see heating, red colors, throughout the full vertical extent of the atmosphere, but we don't. Climate models, these are the latest, greatest climate model simulations that fed into the most recent 6th assessment report of the IPCC in 2021, when they are driven with human-caused changes in greenhouse gases, also show this more effective trapping of heat lower in the atmosphere. And that means that has the inescapable consequence that the upper atmosphere cools. As we're adding greenhouse gases lower down in the atmosphere, we're essentially making it more difficult for heat to reach the upper atmosphere. All models show this basic physics, consistent with the satellite data, inconsistent with the notion that the sun explains all of the surface warming, surface global warming. So this gives you some illustration of the power of patterns here. Now, what are the actual nuts and bolts of fingerprinting? Well, what you can do with climate models is you can also run these world without us simulations where there are no human-caused changes in greenhouse gases, and you can run all the world's climate models for thousands of years of simulated climate and learn something valuable about natural climate variability. So in this case, the fluctuations in atmospheric temperature that are driven by things like El Niños and La Niñas and many other natural modes of variability. The kicker is that when you do that, and indeed when you look at observations too, and at natural variability in the satellite data, natural variability looks nothing like the human fingerprint, this warming low down and cooling up high. The characteristics of natural variability are smaller scale patterns. So you can then do what Hasseman advocated for, You can search for this human influence fingerprint due to human-caused changes in greenhouse gases in the satellite data and quantify that similarity between the human fingerprint and the satellite temperature data. And you can do the same with many, many thousands of years of natural climate variability. So this is the similarity that you might get by chance between those natural variability patterns I just showed you and the human fingerprint of warming low down and cooling up high. This is the similarity that you get when you compare the actual satellite changes in atmospheric temperature with the human fingerprint. The kicker is that it's impossible, virtually impossible, to obtain the observed correspondence between the human fingerprint and the satellite data by chance alone. Natural causes can't generate the patterns of atmospheric temperature change that we are seeing. So just a quick detour here. What is consilience? Wikipedia defines consilience as, quote, the principle that evidence from independent, unrelated sources can converge on strong conclusions. Human effects on climate were predicted a long time ago. This gentleman here, Suki Manabe, back in 1967, used a very simple climate model to predict how the vertical structure of atmospheric temperature might change, work for which he was also awarded part of the 2021 Nobel Physics Prize. And Manabe's prediction, with a very simple climate model, again, we're looking from the surface right to 40 kilometers above the surface, was that when you increase atmospheric CO2, you warm the lower atmosphere and cool the upper atmosphere. And this is what I want to illustrate with consilience. This was a prediction. It was based on sound theory of the heat trapping effects of greenhouse gases. And the observations and models came together with this prediction and basic theory to show Manabe was right. When you increase CO2, this is what we've actually observed: warming low down, cooling up high in the atmosphere. Consilience also involves looking at other types of information, which is what you see here. In yellow, these are satellite measurements of the sun's energy output made from space, at least from the most recent period here, from 1979 through to the present. Prior to the satellite era, these are inferred from sunspots. The kicker is that over the period we've measured the sun's energy output from space, it hasn't increased, but global mean temperature has increased. Again, this is a fundamental difficulty you face if you posit that all of the global warming at the surface that I showed you in an earlier slide is purely natural and it's just due to the sun. It can't be. You have these two fundamental difficulties. Sun's energy output isn't increasing, global temperature is, and the stratosphere is cooling, not warming, as it would have to if all surface warming were due to an uptick in the sun's energy output. So back in 1995, those 12 words, the balance of evidence suggests a discernible human influence on global climate, were criticized. And one of the lines of criticism was, you're only really looking at temperature. If there is a human-caused fingerprint lurking in observations, it should be manifest in many, many different variables, not just in temperature. Since 1995, hundreds of scientists throughout the climate science community have taken that criticism to heart and have looked not only at temperature, but at the changing heat content of the ocean, at atmospheric circulation patterns, at rainfall, at the water vapor satellite data that I showed you in the first slide, at runoff from continental rivers, at things like Arctic snow ice coverage, Arctic snow and sea ice coverage. And the bottom line from all of this work is that the changes in literally dozens of different climate variables are internally and physically consistent. And they're independently monitored with a range of different instruments, measurements made by different groups. That's consilience of evidence. And ultimately, that's what led to the word unequivocal human effects on climate in the 2021 IPCC report. Just finally, I want to say a few words about extreme event attribution, which has received extraordinary attention in the last few years in particular, given extreme events around the world, extreme heat, extreme rainfall and flooding events, wildfire events throughout the world. And many folks in my world are now doing event attribution studies. What are these? Maybe the earliest example of this was with the European summer heat wave in 2003. That involves very unusual warming in Southern Europe during these 2 months, July and August 2003. The warming was over 1.5 degrees Celsius warmer over much of Southern Europe than normal. The estimated excess mortality was 72,000. It was a catastrophic event. Folks at the Hadley Centre for Climate Prediction in the UK decided to look at the likelihood that this event had been affected by human-caused global warming. So what did they do? They ran their climate model with no human-caused changes in greenhouse gases and looked at the likelihood of getting something like the European summer heat wave in 2003. So summertime warming over Southern Europe in excess of about 1.2 degrees Celsius. And they could run their model many thousands of times, and they did. And this was the risk of getting that kind of event in the absence of any human-caused climate change. So in a world without us, without fossil fuel burning, without human-caused warming. And the risk of getting that kind of event, just by chance, was roughly 1 in 1,000. Then they looked at the risk of getting that event when they ran their model many, many times with human-caused global warming over the 19th and 20th century. And the risk fundamentally changed with human-caused warming. Their bottom line conclusion, which they published in Nature in 2004, was we estimated it's very likely that human influence has at least doubled the risk of a heat wave exceeding this threshold magnitude. Since then, folks have done this kind of work with many different kinds of extreme events using a variety of different modeling approaches and statistical approaches, fitting generalized extreme value distributions to data. And the bottom line is that folks are now looking at these kind of questions, not only in the climate modeling world, but also in the legal world. Can we reliably estimate the human contribution to the extreme event's likelihood? Are the key uncertainties in that estimation well quantified? And do we have reliable damage estimates for the extreme event? This is very relevant to the discussions that will be taking place in December at COP28, where loss and damages are going to be part of the discussion. And folks are thinking about how to use event attribution approaches to inform decisions about who is liable for compensating countries for loss and damages they experience due to extreme events. Another thing that's very relevant to those kind of discussions is what fossil fuel companies knew about the reality and seriousness of climate change. This is from a paper published earlier this year in Science that looks at Exxon's internal and peer-reviewed publications about climate change based on climate modeling work that was done at Exxon, based on exhaustive analysis of Exxon's own internal corporate knowledge of how climate change might unfold. The red line here shows you observations of global mean temperature change, and the gray lines are Exxon's own internal predictions. There are 12 of them. Each of them is numbered and they're color-coded. The earlier predictions made by Exxon are lighter, and the later projections, I believe the latest one was made in 2005, are darker. The main conclusion of this paper in Science was that Exxon's internal projections of climate change were skillful, just as skillful as the IPCC's projection, actually. So this kind of information is relevant to discussions about liability, because there was this disconnect between Exxon's public-facing attacks on the reality and seriousness of climate change, even on the 1995 IPCC report, and their internal corporate understanding of the seriousness of the problem. So just finally, take-home messages here. I've tried to show you very briefly that climate fingerprinting uses pattern information to disentangle human and natural effects on climate. It was developed in the late 1970s. One of the key developers was Klaus Hasselmann in Germany. And now, in today's world, human fingerprints on climate are unequivocal and ubiquitous. They're everywhere. They're not confined to surface temperature alone. They're in literally dozens of different aspects of observed climate change. I also briefly at the end mentioned that climate scientists use techniques called event attribute, look at individual droughts, heat waves, floods, and try and make scientifically informed statements about the contribution of human-caused warming and moistening of the atmosphere to the change in the likelihood of that extreme event. Thank you, Kishan, for giving me this opportunity, and very happy to answer any questions you might have.
Thank you, Ben, for such an important session. And we have seen through your session that a pivotal role fingerprint research has played in confirming human-caused fingerprints across the entire climate system. One question, because you were showing in one of the slides, it was quite insightful about the troposphere and the stratosphere that he was showing from 10 kilometers to 50 kilometers with the human caused fingerprints and natural fingerprint. Probably when we have time towards the end, and David is also here, if you could throw some light later in the Q&A session about how machine learning could disentangle the causes of the tropospheric warning as such. And does that reveal anything about the differences between any climate models that you showed, as well as some of the satellite observation as well? So we'll get your views towards the end. And I would like to also welcome David, who has joined us now. And we're going to throw light on climate risk. We have heard a lot of things about it's about the wild and unpredictable stuff that comes with our changing climate, from crazy storm to rising sea levels and messed up ecosystems that we see. We are facing a whole bunch of challenges, to be honest, and figuring out how to deal with all these risks is going to be super important. It's not only about it's about it's about being ready for the unexpected and finding smart ways to protect our communities, economies, and the planet as well. Exploring climate risk isn't just about the problem. It's about finding cool ways, to tackle them. And one of those cool ways is something which David has developed, and through the UNEP FI charter, he heads climate risk for UNEP FI. And I would request David to have a quick self introduction, as well as throw some light on what you're doing in this space and run up to COP28 agenda as well. Over to you, David.
Great, thank you so much, and an honor to be here with Dr. Santer and Kishan with you and the group. I'm David Carlin. I oversee climate risk for the United Nations Environment Programme's Finance Initiative, or UNEP FI. What I'll talk to you a little bit about is essentially our work as UNEP FI, explaining what we do. I'll talk a little bit about climate risks, and then also a little bit about what we sort of see as potentially some of the outcomes and some of the focus areas at COP28 for perhaps better or for worse. So I'll take you through a few different things that really begin with a overview of some of the work that UNEP FI has done, and then we can go into a bit more of a discussion. So UNEP FI is the United Nations Environment Programme's Finance Initiative. And what does that mean? It means we're a small group that works specifically with the financial sector and largely the private sector, although increasingly now we're working with supervisors and central banks as well. I lead the risk program, which has had about 110 institutions participate over the last few years, and about 50 that are in our current phase of work, really from a wide diversity of geographies. And what we really aim to do is try to bring the understanding of climate risks, and increasingly now the understanding of nature-related risks, to the financial community, and really do this in a way that accelerates sustainability. Sometimes we think about how do we differentiate ourselves from, say, an industry group, and the key is that we really are guided by the principles of UNEP, of really supporting sustainability and making this move towards sustainable finance also a move toward financial sustainability. And so we put together pieces on sector risks. So this recent paper was about the real estate sector and potential physical and transition risks posed by it. We also have a tool landscape, which has both a database of the variety of commercial providers, but also others in the open source space. We've worked on transition planning, and I've been a member of the UK's Transition Plan Task Force. And we're also doing work at the intersection of climate and nature through the work of the Task Force on Nature-Related Financial Disclosures. So with that in mind, we are presently looking at a few different areas. The first one is looking at how we use climate tools. And Kishan's been involved with one of my colleagues in helping to advance that, but thinking about what new tools there are to see further than we currently do, to understand better where the challenges exist. The second is understanding the data itself and recognizing that, as Dr. Santer was saying, that these physical risks are not ones that are going away, but also we need to think about how they interrelate to each other. A lot of models make the mistake in the risk side of simply looking at one physical consideration and then forgetting about the correlations and linked and second order effects that come from there. To that point, we're trying to understand and improve climate scenarios. So we're working with a group of central banks on improving the set of scenarios, the practice of scenario analysis, and the role of climate stress testing. We're also interested in, this was mentioned just before, about greenwashing and legal related risks, of understanding where responsibility may lie, what kind of risks may be posed in different sectors, and also how one really acts on their claims of sustainability rather than just saying them. And then we hold a number of workshops with the International Energy Agency on their new pathways, with standard setters on new guidance, with those of our UNEP colleagues on reports like the Emissions Gap Report, which I was one of the reviewers for, and other related documents. So that's a bit about our work and how we work within the financial sector. I'm going to switch now to do a little bit of a discussion of what the overall landscape of climate risks looks like, because I think that that's one of the areas that isn't always fully appreciated. So I'll just switch to to my other presentation here to give you the opportunity to see that. And so if we go
and while you do that, David, also if you could throw some light on some of the working group that you mentioned in the previous slide. If there's someone who's keen to contribute in some shape and form, is there any opportunity for them to work along on those ones?
So with our working groups, depending on what they're working on, there's a potential to explore some of those topics. If any of those particularly speak to you, we're obviously very eager to have you involved and get more connected. So at the end, I'll share my my email. Right now, the program is designed to work with financial institutions and experts. And so if you have expertise to offer or you're looking to connect into our work, there'll be ample opportunities to do so. I think it's helpful, though, to talk about the kind of consequences of climate change as well. And a lot of times, I think we overly narrow these consequences. We think a little bit too much about the sea level rise, about temperature, and then we don't go further, and we don't recognize the diversity of impacts that are already being felt. I think that's the other mistake. Is if one mistake is being too narrow in our understanding of climate impacts, the second is missing the temporal aspect, forgetting that these effects are already being felt now in a world that's over 1 degree Celsius warmer and will only intensify. And these are public health concerns, such as those related to air pollution and the dangers of extreme heat, also the spreads of pathogens. There's also, though, impacts on ecosystem services, the potential collapse of major ecosystems that are critical to providing for our global way of life. There's also shifts in water availability, key resources, both key resources demanded and required. Those also pose some significant challenges and may also increase both geopolitical tensions, but also the potential for internal as well as external migrations. There's also risks that come from severe weather that results from business shutdowns. A lot of times we focus, again, just simply on the physical asset, and we forget about the transportation network or the public health system, and realize that much of the damage and much of the impacts is caused by the disruption in our systems rather than in our particular assets. So I think it's helpful just to give a little bit of a kind of typology of what sort of risks the financial sector talks about, because I think they're helpful classifications. So the first classification splits into transition risks and physical risks. Transition risks are ones that are the result of the need to shift to net zero. And while that is scientifically necessary, it will also involve an unprecedented amount of economic shifts and change. As a result of that, there's potential risks that result that companies that are unaware or lagging behind may be disrupted. And so that can come from the way we break those down into policy, technology, and market risks. The market risks are ones caused by changes in preferences. So say a shift in consumer preferences away from meat and toward a more vegetarian diet may have impacts on a company that produces beef. Another example may be shifts from investor preferences of those that are investing in long-term fossil fuel projects may begin to have their doubts of whether there will be much need in 2040 or 2050, and they may cancel some of their funding to those projects. Again, another market-related risk. We also see the technology-related risks, and those are the fact that by having a transition, we're seeing new technology replace old technology. And this is a good thing. But if you're a financial institution who is currently holding the assets of another institution that is a high emitter, this may not be actually such a great thing for your balance sheet. Finally is the idea of policy risks. As governments begin to take the climate crisis more seriously, they're increasingly recognizing that policies like carbon pricing, cap and trade, and other systems that will shift the balance away from fossil fuels toward renewables and toward low carbon are ones that are both desirable and necessary. But certain business models are not going to be adapted to that and will not survive. And so knowing whether your business or that which you've invested in is in that second category is particularly important. On the other side, getting back to physical risks are probably the more intuitive ones we think about when we think about climate change. These are the types of risks that fall into the bucket of what happens due to climate change. And so we tend to think of them in two ways. One are what are called incremental risks or chronic risks. These are the shifts in the baseline or the change in the mean. So this is rising sea level, this is warming average temperatures. Whereas the acute risks or the extreme events, these are the ones that make the headlines, but they really are intimately related. And as you saw in the prior presentation, the influence of warming by shifting the means, by making various events more volatile, really does change the odds. And it means that we are playing with a loaded die. And so we have to think about the extreme events, the record heat waves, the stronger storms, as the consequences of those shifting incremental risks as well. The two really link together. For those of you more statistically minded, this is kind of the breakdown of means and extremes. So wanted to give you a bit of that overview. And then as we look ahead to COP28, I'll just mention a few things that I think are probably top priority there. Of course, this is the second year that COP is in the Middle East in a row. It's in a major oil producing state. And one of the challenges is going to be how do we ensure and retain the legitimacy of the meeting in that context? And one of the things that we're potentially cautiously hopeful of is a growing focus on adaptation. Adaptation presently is only about 10% of total climate finance, and yet adaptation is not about securing a better future. It's about protecting people in the present and today. And so if the potential deflection that we see on fossil fuels because of where the embedded interests lie, while that is, I think, going to be one of the more frustrating things over the coming couple weeks, we're hoping that at least there's going to be a significant push and a significant move towards scaling up adaptation finance. At the same time, we saw at COP27, the crowning achievement in Sharm el-Sheikh was the creation of the Loss and Damage Fund. And I've been saying the last year that there's less than meets the eye there because the fund doesn't have any funding. It doesn't have designated recipients. It doesn't have designated payees. It doesn't have claim conditions or payment conditions. And so essentially it's the sort of proposal to begin a proposal. And so we're hoping that some of those lines begin to fill in on the map as far as who can be eligible, what sort of initial contributions would look like, what kind of payouts could occur. But one of the other themes that I think we're going to see at COP this year is the continuation of what's called the Bridgetown Initiative. And the vision there with Bridgetown started by Bridgetown being the capital of Barbados. Mia Mottley, the Barbadian Prime Minister, she had put forth the idea that we really need to rethink global finance and we really need to rethink development finance. And I think that that is absolutely right. The current systems of the World Bank and the IMF have been increasingly shifting toward climate in their development funding, but clearly it has been shown that this isn't going to be sufficient alone. And so we need public-private partnerships. We need a rethinking that doesn't trap countries in debt. And so the re-architecting of the financial system that was really set up after World War II, 80 years ago, is going to be very much on the table. My expectation is very little concrete will get done on that, but a lot of discussion will get done. My expectation is more of that will occur at the IMF and World Bank spring meetings in Washington in 2024. But look for that as a theme, look for adaptation as a theme, and really, hold people's feet to the fire on the loss and damage to really make sure that we have something tangible that comes away from that. So that's a little bit of a rundown from how I see it. And, Kishan, thank you again for having me, and I'll hand back to you for perhaps, a few questions or wrap up as well.
Perfect. Great. Thanks so much. And, it is so important. I've been saying this, if we would have mitigated what we had to mitigate 20 years back, we didn't have to adapt to it now. And the way things were, especially, with the politics around the NDAs and the NDEs and how the projects are prioritized based on the GCF funding, two NDAs as per the alignment that has been agreed upon. Loss and damage funds are not that structured at this point in time. So, it's one of the critical challenge that we see in this space. I'm gonna go back to Dr. Ben first, and then again come back to you, David, for a question, which is again more or less in the same lines about the innovation strategies and the adaptation that you would want to prioritize to address some of the multifaceted challenges posed by climate risk in ensuring resilience as well as safeguarding against its diverse impact. But before that, if I could request Dr. Ben to unmute yourself, and there's a question which Penty Lotfian, if I have pronounced your name correctly, has asked. If you want to unmute yourself, Penty, and ask the question to Dr. Ben directly, you're more than welcome.
Hello. Thank you very much for such a excellent session, both to Kishan and both speakers. Thank you. Actually, my question was really that regarding the fingerprinting that you spoke to. Can we discern between different human fingerprints, i.e., is this CO2, is it other gases, is it something else, so that we can consider the quantitative effect of each to make more, we can say, granular decisions? And also part of that is that obviously because fossil fuels are part of the biggest problem, the whole focus on that focuses on reduction of fossil fuel use. However, on that trajectory, we are actually moving to a material heavy economy, and we are mining the earth like there is no tomorrow. And that has also for sure some impact. Would fingerprinting be able to show or work with, say, showing the impact of mining on the climate? Because I am by no means have no expertise on climate science, but working with technologies and all of this, I can sort of in general guess that mining is not going to be without impact.
Thank you very much for that question. Let me try and unpack it by first saying that, as I showed in one of my initial slides, different human factors that affect climate have different characteristic fingerprints. And we could see that for human-caused changes in heat-trapping greenhouse gases, for human-caused changes in particulate pollution associated with things like sulfate aerosols. So yes, it is indeed possible to use that pattern information to try and estimate what the contribution of different individual human and natural factors is to observe climate change. And the IPCC actually did that in the 6th assessment report. They have a couple of nice figures in there that I'd be happy to share with you later, where they attempt to do that kind of quantification based on the application of fingerprint methods, and also based on other simpler methods. Our best understanding is that human-caused changes in greenhouse gases are responsible for virtually all of the observed global warming since 1850, and that human contribution through burning fossil fuels and increasing greenhouse gases is partly offset by the cooling of particulate pollution. And again, I'd refer you to that figure for a quantitative breakdown of individual factors. But the bottom line is, yes, we can and are actively trying to make that quantification. And getting back to your question, Kishan, machine learning is helpful in doing that because you can process huge volumes of pattern information from essentially all of the world's climate models in order to very efficiently try and estimate and quantify uncertainties on individual contributions to climate change. I'm not really competent to answer your question about mining and the specific emissions associated with that. That said, we do now from space monitor things like methane and monitor CO2 emissions. we have the capability to assess the contributions from individual sources to greenhouse gas emissions. And that capability is going to be extremely important going forward in assessing the contribution of different nation states and different sectors to the emissions that are partly responsible for human-caused climate change. I don't know whether that answers your question, but maybe David has a better answer than that.
Yeah, thank you very much. Yep. Please, David, if you have anything.
No, I think that captures the view very well. From the responsibility side, there is some really great work going on in attribution science that Dr. Santer mentioned, and that is going on at Oxford and in a number of other places. I think, and again, not taking a purely legal perspective, but having folks on my team who lead our legal work, what I would say is I think that those things are still a little ways away from the apportionment of responsibility. There was an important case that was a bit of a watershed a few years ago, where a Peruvian farmer actually sued the German government for their share of emissions, and I think that that's an important test case. While the German court ruled that was unenforceable, the initial local judgment was one that does show a potential way forward. I think one of the challenges is going to be how that global responsibility will change over time as emissions continue from certain countries. And so in some cases, part of the goal is to recognize the debt that we owe and the responsibilities we have. And I think the Paris Agreement really aspires to do that. That's why Article 8 is about loss and damage. Articles 9 and 10 are about financial and technology transfer, because the goal isn't to reach an equality of historical emissions. That would be disastrous for the planet, but rather to help reach a higher level of development while avoiding following that same emissions trajectory. And so we're looking at a number of mechanisms to do that. Of course, the legal one is certainly one of them.
Great. Thanks, Ben and David, for that response, and thanks, Betty, for your question as well. We have overrun by 5 minutes, but we started 10 minutes late because of a glitch in our technical glitch as such. But I'm just going to close with one last question to David, to yourself, and then just a brief closing remark. And I apologize for the overrun here. My question again, David, going back to the same thing, because in our bid to ensure resilience and to safeguard against all the diverse impacts that that is posed by climate risk, then what strategies or what adaptation do you prioritize in this bid as such that you have seen, or you have any views that you would like to share?
Yeah, I have pretty strong feelings about this, because I think there's a lot of brilliant work being done with analytics and big data, AI, and many other things that is really exciting and important. And yet I say that work is valuable for early warning systems. That work is valuable for optimizing both in the mitigation space and in predictive modeling. But at the end of the day, from more of a development standpoint, which is a little more of the financial background that I would take, we kind of know the things that save lives. And it isn't about whether a seawall is 7 feet or 8 feet. It isn't about whether a set of homes is set back 40 meters or 50 meters. It's really about the integrity of critical services. So is the electricity grid reliable and resilient under stress? Is the health system reliable and resilient? Is transportation accessible? Are there warning systems in place? And is there public trust? And so, not to say that those important and fancy analytics don't matter, but just to say one of our core problems is sometimes losing the kind of specifics of what we need to do. When we think about disasters in different parts of the world, much of the outcome falls down to these specific factors, not based on just the potential of what extreme value is taken on. But even a fairly modest flood can be devastating in a place that doesn't have good health resources, can be devastating in a place where there is potential limited transportation options. And so we see this time and again in who is most vulnerable and who is most affected.
Great, thanks for that response. So on that note, I mean, the session is recorded, so we will share, with all the people who are not able to join, who shared the messages and they were not able to join in as well, and we'll have them, go through this, recording as well. So thank you. I just want to thank everyone who were able to join, and special thanks to Dr. Ben and David, to you both for giving your time to sharing your views. Thank you.
Absolutely. My pleasure, Kishan.
Thank you very much. Keisha.
Have a good
Thank
weekend.
you, everyone.
Bye-bye. Bye. Bye.
Thank you so much.
Thank you. Bye.